Welcome to this explainer. Today we're going to pull back the curtain and really break down the invisible but absolutely massive infrastructure powering modern artificial intelligence. Think about it. Every single time you chat with an AI or generate a cool image or run a predictive model, there is literally a sprawling digital city working tirelessly in the background for you. And I promise, stick with me and you'll easily pass the test of understanding cloud AI by the end of this session. Okay, let's take a quick look at our roadmap. We're going to start with big data and modern AI. Then, look at the cloud computing shift, scaling infrastructure, distributed storage, and the CAP theorem, MapReduce for processing at scale, and finally, cloud security and governance. Let's dive in. To really set the stage here, we've got to face a hard physical reality. Standalone computers have strict physical limits, right? They're constrained by their motherboards and silicon architectures. So, when a single computer hits its physical ceiling on local RAM or CPU clock cycles, we have to ask ourselves, how on earth do we handle this massive scale? Well, the answer is distributed execution.
Which brings us to Section 1, Big Data and Modern AI, the data problem.
To systematically tackle massive data workflows, infrastructure engineers lean on a really helpful framework known as the 5 V's of big data. You simply can't build a functioning AI system without addressing every single one of these branches.
Let's break these down real quick. Volume is exactly what it sounds like, the sheer physical magnitude, moving from gigabytes up to multi-petabytes for deep learning. Velocity is your data speed. Variety is the structural layout. Veracity is all about trustworthiness. And value? That's the actionable intelligence you actually get at the end. Now, what's fascinating here is how modern AI flips the script. Historically, volume was the biggest headache. But with AI, the complexity heavily shifts to variety, handling unstructured stuff like voice tracks and images through complex tokenization. It also hugely shifts to veracity. If your data is full of mislabeled parameters, your upstream models will completely crash and burn thanks to noisy gradients and data drift.
All right, moving to Section 2, the cloud computing shift, redefining operations.
Back in the day, building a data center meant huge upfront capital expenditures, or CapEx. You literally had to buy the physical servers upfront. But cloud computing, it shifts this entirely to operational expenditures, or OpEx. So the crucial takeaway is that the cloud moves us away from buying expensive permanent hardware to just renting infinite elastic resources by the millisecond. It gives you the illusion of unlimited computing power without laying down a massive chunk of cash on day one.
Because of this pay-as-you-go model, we run into a fascinating mathematical reality. Check this out. Running 1,000 servers for 1 exact hour costs you the exact same base charge as running 1 server for 1,000 hours. This is absolutely game-changing for AI. It totally democratizes access to supercomputing-grade hardware, meaning your data science team can execute massively parallel fine-tuning jobs in a fraction of the time, and there's zero scale premium.
And this elasticity solves a massive historical nightmare. The guessing game. Traditional hardware forces you to guess your demand way in advance. If you guess too high, you're over-provisioning, wasting your budget on servers that just sit there collecting dust. But if you guess too low, you're under-provisioning. In the AI world, under-provisioning is catastrophic. It means your compute capacity gets completely saturated and your real-time inference APIs will literally crash right when user demand spikes. No thank you.
Let's head into Section 3, Scaling Infrastructure for AI. Architecting for growth.
So your AI workload is blowing up. What do? Well, you basically have 2 choices. Vertical scaling, which is scaling up, means making a single machine beefier, like upgrading from a 16-core to a 128-core CPU. Think of it like swapping a bigger engine into a single delivery truck. It avoids network lag, but you'll eventually hit a hard physical limit. Horizontal scaling, or scaling out, means adding multiple independent computers to the network. This is like buying a massive fleet of smaller delivery vans. It gives you endless scaling for sure, but it definitely introduces a lot of network complexity.
To actually make that massive fleet of vans work smoothly, software architecture had to evolve. We moved away from monolithic architectures, where all the code shares the same memory and CPU in one giant package, to microservices. Microservices break the system down into decoupled, single-purpose services that talk to each other over lightweight interfaces like REST APIs. For AI, this is a lifesaver. It lets your team scale up just the compute-heavy inference endpoints without having to mess with the upstream data parsing nodes at all.
So let's see how all this translates into the real world with 3 main cloud archetypes. Infrastructure as a Service, or IaaS, gives you raw virtual hardware. That's perfect if you're doing custom CUDA compilation and deep hyperparameter tweaks.
Platform as a Service, or PaaS, handles the underlying patching and containers, leaving you to just manage your code, which is awesome for auto ML pipelines. And finally, Software as a Service, or SaaS. That manages the entire pipeline top to bottom, offering you pre-trained black box inference calls over super simple APIs.
On to Section 4, Distributed Storage and CAP, Managing Data Nodes.
This brings us to the infamous CAP theorem. When you're managing data across a network, you're juggling three things: consistency, every read gives you the most recent write; availability, every working node returns a response, even if it's slightly out of date; and partition tolerance, the system keeps chugging along even if network messages get dropped. Now, because physical networks will drop messages, it's just a reality, partition tolerance is non-negotiable. You have to have it. Therefore, the theorem says that during a network outage, you must make a hard choice: absolute real-time consistency or total system availability. You can't have both. A classic example of a system that completely prioritizes consistency is HDFS, the Hadoop Distributed File System. It uses a coordinator participant model. Right in the center, you have the name node. That's your master coordinator holding all the metadata mappings directly in RAM. Then you have the data nodes. These are the storage participants that actually hold the segmented data chunks on their local physical disks, and they're constantly pinging health heartbeats back to that name node.
Now, hardware breaks all the time. So to make sure your precious AI training data survives a catastrophic server crash, HDFS uses a brilliant automated block replication pipeline. It defaults to exactly 3 copies of your data. Copy 1 goes to a local data node in your home rack, copy 2 gets shipped off to a distinct data node in a remote secondary rack, and copy 3 goes to a totally different data node that sits within that same secondary remote rack. This rack awareness means your data survives even if an entire network switch just literally goes up in smoke.
Next up, Section 5, MapReduce, Processing at Scale.
So how do we process all that stored data? MapReduce is essentially a genius 4-step recipe that hides all the messy complexities of partial machine failures. First, it segments your data along those HDFS blocks we just talked about. Second, map execution tasks transform that data into intermediate key-value arrays. Third, we have shuffle and sort, which groups everything together using deterministic hash functions so matching keys land on the exact same machine. And finally, reduce execution aggregates those lists to construct your final clean output.
But this is where it gets really clever. What happens if a server isn't dead, but it's just running super slow and threatening to bottleneck your whole AI pipeline? MapReduce uses something called speculative execution. If a task starts lagging behind the average progress, the coordinator doesn't wait around. It literally creates a race. It schedules an identical duplicate task on a completely healthy, independent node. The first one to finish wins, and the slow duplicate is instantly terminated. How cool is that?
Finally, we arrive at Section 6, Cloud Security and Governance, Protecting the Model.
When you're dealing with highly regulated AI architectures, think clinical medical imaging or financial data, you really don't mess around. Engineers use strict, explicit role permission matrices. So, for example, a physician or a nurse can view raw charts and modify patient info. But an AI researcher, no way. They can only analyze de-identified data. Meanwhile, the IT admin can manage the overarching cloud config, but they have zero access to any actual patient data or the research environments.
What we just looked at is a textbook application of the principle of least privilege. This basically mandates that every user, machine account, or automated process gets the absolute bare minimum access rights required to do their job, and nothing more. When you combine this with heavy-duty cryptography like AES-256 encryption at rest and hardware multi-factor authentication, it ensures an AI researcher can't accidentally nuke the network routing, and an IT admin can't snoop on proprietary training data.
All right, you made it. You survived the explainer and successfully navigated the insane physical and digital realities of cloud infrastructure. But, understanding how data moves from a single silicon motherboard to a globally distributed microservices-driven network leaves us with one incredibly vital question to ponder about our future. If cloud computing gives us infinite scaling simply by shifting our massive service to someone else's physical data center, who ultimately controls the invisible keys to your data's intelligence? Thanks for joining me on this deep dive, and keep questioning the architecture that powers our world.